Hello everyone, my name is ABHIK BHATTACHARYA and my registration number is 17BIT0276. Today I am making a video on the course Computer Architecture and Organization. The course code is ITE2001 and the slot is A2 and the name of the professor is Professor Alagiri I. So in this video I'll talk about binary addition, binary subtraction and binary multiplication. So thanks to you all for being here and please enjoy the video. First we'll have a look at sign, magnitude, addition and subtraction. I have taken 8 cases where 4 are of addition and 4 are of subtraction. Let's look at the first case. In first case we have taken A as positive and B as positive. So the answer will be plus of A plus B. In the second case we have taken A as positive and B as negative. So if A is greater than B, the answer will be plus of A minus B. If A is smaller than B, the answer will be minus of B minus A, and if A and B are equal, the answer will be plus of A minus B. In the third case, we have taken A as negative and B as positive. In this case, the answer will be, when A is greater than B, the answer will be minus of A minus B, and when A is smaller than B, the answer will be plus of B minus A, and if A equals to B, the answer will be A minus B. In the fourth case, both A and B are negative. So the answer will be minus of A plus B. So these 4 were the cases of addition. Now we'll look at the rest 4 cases of subtraction. In the first case, we have taken both A and B as positive. So if A is greater than B, the answer will be plus of A minus B. If A is smaller than B, the answer will be minus of B minus A. And if A and B are equal, the answer will be plus of A minus B. Now when A is positive and B is negative, the answer will be plus of A plus B. And in the 7th case, we have taken A as negative and B as positive. So the answer will be minus of A plus B. And in the final case, we have taken both A and B as negative. So when A is greater than B, the answer will be minus of A minus B. When A is smaller than B, the answer will be plus of B minus A, and when A and B are equal, the answer will be plus of A minus B. Now we'll have a look at this circuit. We have 2 operands A and B which are stored in these 2 registers, and their sign bits are stored in AS and BS. Now let's take the case of addition. In addition, the value of M, that's the mode bit, is determined using XOR of AS and BS. When AS XOR BS is 0, this circuit is in addition mode. So the complementer won't work and the input carry and mode bit have equal values. So input carry will be 0. Therefore A will come as it is and B will come as it is as well. Since the complementer is not working, therefore A plus B will store the result, and if there is an output carry, it will go to the E register which stores the output carry, and which will later go to AVF, which is the output like the overflow register for A plus B. Now in the case of subtraction, one of these will be negative, one of these will be 1. So the XOR will be 1. Therefore M will be 1, M bit will be set to 1 and input carry will be 1 as well. Therefore in this case the complementer will work. So from the A register, A will come to the parallel adder, and B will pass to a complementer where it will become B dash, and it will come to the parallel adder and the input carry will be 1. Therefore the final expression will be A plus B dash plus 1, which is A minus B, and it will store the value in the parallel adder. Now let's look at some examples. In this example we have taken plus 7 and plus 3. So A is plus 7, it can be written as 0 1 1 1, and B, which is plus 3, can be written as 0 0 1 1. So the sign bit of A is 0 and the sign bit of B is 0. In this case A XOR B will be 0, therefore M 0 and input carry will be 0, so the complementer won't work. Therefore A will come as it is, B will come as it is. So the expression will be 7 plus 3, which is 10. So we get the answer 10. In this example, we have A as plus 7 and B as minus 3. So A, which is plus 7, can be written in the form of 0, 1, 1, 1, and B, which is minus 3, can be written in the form of 1, 1, 0, 1. Therefore, AS is 0 and BS is 1. By AS XOR BS, we get 1. Therefore, the mode bit will be 1 and the input carry will be 1 as well. So AS will come as it is to the parallel adder and BS will pass to the complementer, which is now working. Therefore, B will turn to B dash and it will come to the parallel adder, and the input carry, which is now 1, will come to the parallel adder. So the overall expression will be A plus B dash plus 1, which is basically A minus B, which we will get as 7 minus 3 is 4, which is 0, 1, 0, 0. Thus, we see that this circuit works for both addition and subtraction. Now, finally, we are going to have a look at the flow chart. Now, for add operation, we have AUGENT and ADDEND, which is A and B. And for the subtract operation, we have minuend and subtrahend, which is A and B as well. Now, first, to do any kind of operation, we will compute the XOR of both the sign bits of AS, that is AS XOR BS. Now, if AS XOR BS is 0, so for the add operation, if AS XOR BS is 0, we'll perform addition, but if AS XOR BS is not 0, that is 1, we'll go to the subtraction part. Similarly, for the subtraction part, if AS XOR BS is 0, we'll continue in the subtraction part, but if AS XOR BS is not 0, that is 1, we'll go to the addition part. Now let's have a look at the addition. So when AS equals to BS, we'll just compute the value of A plus B and store it in EA, and the carry that is generated, that is stored in E, will be moved to the add overflow register, and this way we get the final result, which is stored in A and AS. Now in the subtract operation, when AS equals to BS, first we compute A minus B, that is A plus B's complement, which is B dash plus 1, and store it in EA, and we set the add overflow register's value as 0. Now after computing this, if we get E equals to 1, then that means A is greater than B. Now if the greater than or equal to B, if the final value, that the result that we get, is not equals to 0, then the result is stored in A and AS. But if the result that we get is 0, then that means both are equal. For that case, we have to set the AS register as 0, and then we finally get the result in A and AS. In the other case where E is not equal to 0, that means A is less than B. For this, we have to do A's complement. So A's 2 complement. So first we turn A into its complement, and then we add 1, which is basically 2's complement, and we complement A's sign register. So AS is converted to A dash, and then we finally get the value, which is stored, the result, which is stored in A and the AS register. This way, both addition and subtraction operation are performed using a simple circuit. Now let's have a look at sign magnitude multiplication. For this, we'll look at an example where we have taken 13 as the multiplicand and 11 as the multiplier, where multiplicand is denoted by M and multiplier is denoted by Q. So the binary of 13 is 1101 and the binary of 11 is 1011. So to multiply, first we will multiply 1101 with 1, which we'll get as 1, 0, 1 and 1. Then we multiply M with 1 again. We'll get 1, 0, 1 and then 1. and then we'll multiply m with 0, which will give us 0 0 0 0, and then we'll multiply m with 1 again, which by which we'll get 1 1 0 1. Now we just have to add these. So after addition we get 1 0 plus 1 1, 1 plus 0 plus 0 1, 1 plus 1 plus 1. We'll have 1 in carry, and this one will come here. So that 1 in carry will add with this one, which will give another 1 in carry, and we'll get here 0, and then that carry 1 plus this one will give us 0, and the one which is in carry now will add with this one and give us 0, and therefore carry 1, which will give us 1 0 0 0 1 1 1 1, that is 143, which is the product. Flowchart for signed magnitude multiplication. Here we see a flowchart for the signed magnitude multiplication. We take the multiplicand in B and the multiplier in Q. We set AS as QS XOR BS and QS as QS XOR BS. Then we set A equals to 0 and then E equals to 0 and sequential counter as n minus 1. In this, we have taken, for this example, we have taken the multiplicand as 23 and the multiplier as 19, whose product gives us 437. So multiplier 19 is represented as 10011 in binary, and multiplicand 23 is represented as 10111 in binary. So we have taken E, A, Q and sequential counter. According to this, when the value of Qn, that is the last bit of the multiplier, is 0, we shift EAQ to the right by 1 and decrease the sequential counter. And when the last bit of the multiplier is 1, we add A plus B and store it in EA, and then we shift EAQ to the right by 1 bit, and we set then we decrease the value of sequential counter by 1, and we continue this operation till sequential counter has reached a value of 0, and which gives us the product in A and Q at the end. So we have set E as 0, A as 0, Q the multiplier value 1011 and sequential counter 101, that is 5. First, we see that Qn is 1, so we will follow these rules. We will add A and B and store it in EA. So we are adding 0000 and 10111, we get 10111. So that is, after this we shift everything to the right by 1 bit. After shifting, we see that Qn is 1 again, so we'll follow this route again and we'll add 10111 to 01011, that is A. After addition, we get 1000010. Now we'll shift everything to the right again. After shifting, we see that Qn is 0. So in this case, we don't have to perform this addition operation. We can just shift it to the right and decrease the sequential counter. So we do that exactly. So we just shift it and decrease the sequential counter. Again, we have encountered Qn as 0. So we again follow this simple operation of shifting to the right and decreasing the sequential counter. So we do that. And now we are left with 1 in Qn again. So we'll have to add this time. So we'll add 10111 to A, that is 00100, which gives us the answer as 11011. After this, we shift everything EAQ to the right. After shifting, we get 01101 in A and 10101 in Q, and this is our product. Since it says product is in A and Q, so this is 437 in binary. So by this method, we can multiply two signed numbers in their binary form and get the answer. Now let's have a look at boot multiplication method. This is the second way of multiplication where the sign bit is inculcated in the number itself. If the numbers are given in binary form, then we can apply boot multiplication algorithm directly, but if they are given in decimal form, we have to convert them to binary form first, and we have to find the 2's complement of the negative numbers. If both the numbers are negative, we have to find the 2's complement of both the numbers. So the multiplication is stored in BR in this case, and the multiplier is stored in QR. And for this calculation, we have to find the 2's complement of the multiplicand. For that, we'll find the complement of BR and add 1, which will give us the 2's complement. Now, for this operation, we will set AC equals to 0 and Qn plus 1 as 0, and the sequential counter will be equal to the number of bits in the multiplier or multiplicand, whichever has higher number of bits. Also, we need to make sure about one thing, that both the multiplier and multiplicands should have equal number of bits, equal number of bits, where the number of bits should equal to the number of bits in the number which has higher number of bits. Hope that makes sense. So let's have a look at the algorithm. The algorithm says that there's a if condition which depends on the value of Qn and Qn plus 1. If Qn and Qn plus 1 is 0 and 1, we'll add BR to AC, and then we'll perform arithmetic shift right on AC and QR and decrement the sequential counter. If Qn and Qn plus 1 is 0 0 or 1 1, at that case we'll perform arithmetic shift right on AC and QR and decrement the sequential counter. When Qn and Qn plus 1 are 1 and 0, in that case we'll add AC and the 2's complement of BR, and then perform arithmetic shift right of AC and QR and decrement the sequential counter by 1, and we'll keep performing these operations till the value of sequential counter reaches 0, which will give the result at the end. So let's have a look at this example where we have minus 9 as the multiplicand and minus 13 as the multiplier. So we have 9 in the form of minus 9 in the form of 1 0 1 1 1, and the 2's complement of minus 9 is in the form of 0 1 0 0 1, and the multiplier minus 13 is in the form of 1 0 0 1 1. So we have set AC equals to 0, QR equals to 1 0 0 1 1, Qn plus 1 equals to 0, and the sequential counter as 5. Now we check Qn and Qn plus 1. We see that it's 1 and 0. So we'll perform this operation where we add AC and the 2's complement of BR. So after the addition of AC and the 2's complement of BR, we get 0 1 0 0 1, and then we have to perform arithmetic shift right of AC and QR. After performing arithmetic shift right, now we find that Qn and Qn plus 1 have values 1 and 1. So in that case, we just have to perform arithmetic shift right and decrement the sequential counter. So we'll do that, and now we have Qn as 0 and Qn plus 1 as 1. In this case, we'll add BR to AC. So after addition, we have AC as 1 1 0 0 1. Now we'll perform arithmetic shift right. We perform arithmetic shift right and decrement the sequential counter by 1. We see that Qn and Qn plus 1 are 0 0. So in this case, we'll perform arithmetic shift right. After performing arithmetic shift right, we find Qn and Q1 plus 1 as 1 and 0. So for this case, we'll add AC and the 2's complement of BR, which gives the value of 00111 to AC. Then we perform arithmetic shift right, and now the value of sequential counter is 0, which gives us the result 00011 and 10101, that is 111, that is 117. So by this method we are able to find the product of two negative numbers or any numbers even when their sign bit are inculcated in themselves.